So the question is this, for this element, is there more than one inverse? Like, could there be, well, I'll use the same notation as the text, right? So let I'm going to try a new pen. I think this one is drying. So let y and y dash be inverses of A. Okay, so we're going to assume that there are two of them, and we will do a similar kind of proof and actually show that these two inverses are the same, they're equal. So y and y dash are the same. In just the same kind of way that we proved for theorem 11 that there's only one unit, right? So we will show for each element, a random element from the group, that its inverse is unique, right? So that's theorem 12. All right, and I'll use the same notation as the textbook. So instead of talking about A inverse, we'll write it this way. So instead of talking about A, we'll talk about X. So X belongs to G, and there is an inverse, so Yx equals Xy equals E. Right? That's the inverse for X. Y is the inverse for that element X. All right? Now let's assume that there's also another inverse, call it Y dash. Okay? And we will try to prove that Y and Y dash are the same. So I've quite a few steps, and let's see. So theorems 11, 12, down to, I don't know if I'll do the last few. It gets a bit abstruse at towards the end of the chapter. But anyway, there's potentially 10 theorems, so quite a lot to do. Okay, now we'll try to prove that Y and Y dash are the same. Okay, so Y dashed, we'll start here. So Y dashed is just Y dashed E, right? And you may ask, well, why did I do that? But, well, it works. We're trying to prove that that and that are the same. So we're trying to prove that Y dashed, we're trying to prove that this second one is actually the same as the first one. So now Y dashed is just Y dash E, right? That's the unit. That's true. All right. So we can rewrite this a little bit using the multiplicative notation. Now E is XY. Right? Here. There it is there. So E is XY. Okay. Now it's a group, right? And here we have the product of three elements of the group. Now remember, this is shorthand. If I wrote it out in fully, there would be a little circle here and a little circle here. Now these three elements are from a group, so they are associative. So I can rearrange this. I can write this as Y dash X Y, right? By the property of associativity, because it's a group. Associativity is one of the four properties that a group has. Okay. All right. So now, what is this? Right. Now, what is Y dashed? Well, we assumed it was another inverse of X, right? So this is just E, right? So that's E, Y. Now, it's the unit, so that's just Y. And there it is. So we've shown that Y dashed is Y. In other words, for each element, x, is only one inverse. So the inverse of an element of the group is unique. Okay, so that's theorem 12. Okay, now we pick up the pace a little bit. Now there are four properties here. Now, interestingly, some groups have an extra, sort of special property, and here it is. So if AB, or A circle these, if AB is BA for all AB, for every pair belonging to group, if that's true, and in many cases it's not true, but there are special groups that do have this property. If the group does have that property, so for every possible pair, you can reverse the order and it stays the same. They're equal, so AB equals BA. If that's true, the group is said to be abelian. A-B-E-L, abelian. And this adjective comes from the name Abel, who was a famous pioneering group theorist in relatively early, I guess, 1800s. It's the same Abel as in Abel Prize, A-B-E-L Prize, Abel Prize. Now, I've mentioned that, I think, in an earlier lecture, but if you've forgotten or you've not heard of it, for decades, the pure mathematicians were complaining that there was no Nobel Prize for mathematicians, and the reason for that is that Nobel himself just wasn't very interested in mathematics. He's more of an engineering chemist type. He invented dynamite, which revolutionized warfare and engineering, and he just wasn't a mathematician, not very interested. Now there's a story, and that's all it is, it's a fairy tale, it's not true, that the reason why he rejected the idea of awarding his prizes also to mathematicians, besides medicine and physics and chemistry and literature and peace and whatever, was that his wife had an affair with a mathematician. Now that's a fairy story because Nobel was a bachelor. Okay, so that kills that story. Okay, but it's an interesting story. Okay, now Abel pioneered, we'll go into it later at master's level. Abel did some significant work in very early group theory, and he was Norwegian. And now, after decades of complaints by the mathematicians, finally the Norwegian government actually did establish the equivalent. They couldn't call it a Nobel Prize because that would go against the will, the will and testament of Nobel. But in practice, it's effectively the same. Like the amount of money is pretty much the same. The prize-winning amount of money per year. It's won every year, just the same way as Nobel Prizes are won. And it was started in 2003. So a Frenchman called Serre, S-E-R-R-E, was the first. Serre. He's a genius mathematician. And these Abel prizes have been won every year. So he was the first. Okay, so it's the same Abel in the word abelian, and an abelian group is commutative. Like you can commute these two. In other words, swap the order. You can commute them. So an abelian group is a commutative group. Same thing. It's just two different labels for the same concept. Okay. So abelian is just the same thing as commutative. Commutative. Now we talked about commutative operations in an earlier lecture as well. Okay. So I will wipe all this out, and then we'll start on the right hand side of the board. So I'll stop there for a moment.